So what we're going to be looking at now is the definite integral, and we're going to set up the definite integral as a summation, as a limit of summations. And it's one of the trickier concepts in all of integration. Basically what it does is it sets out how the integral actually is a collection or an accumulation of all of these small rectangles, right, underneath the curve, all right, and it shows us how we can do that mathematically. So we define the integral as an area under the curve on a particular interval, and we estimate it using rectangles, like this picture right here. Okay? As we increase the number of rectangles we use for the estimation, we're going to get a better and better estimation. Okay? And so it's that idea, right, that as we increase the number of rectangles, we get something closer and closer to the actual area underneath the curve that actually allows us to have the definition of the definite integral. So let's look at first the idea of the Riemann sum, or this idea of how do we find the area using these rectangles. So the first thing that I did was I wanted to break up the rectangle or the area under this curve, say from A to B, into n different regions. Okay, so for example, let's do this one. We'll do it 1, 2, 3, 4, 5, 6, 7. So we've got 8 regions. 1, 2, 3, 4, 5, 6, 7, 8. So what we would do is we would say, okay, well, our delta x is going to equal b minus a divided by, in this case, 8. That's our delta x. Now, what I'm going to want to do is I'm going to want to eventually increase the number of them, and I want to do that arbitrarily. So I'm going to actually make delta x equal to b minus a over n. And that's going to allow me to actually increase the number of rectangles to as many as I want and eventually to make it up to infinity. So that's going to be my delta x. And delta x is this size. So just as a reminder, that's what that is. Then I've got two values, okay? One is the values of each one of these x's. We're going to call them xi, or xi stars. And we'll use right endpoints. Okay, so right endpoint. So this one right here, the first one, is a plus delta x. Okay, because we've got delta x is the distance from A to this first line, and then we're going to start at A, so A plus delta x to get me to the first right endpoint. To get to the second right endpoint, okay, it's going to be A plus 2 delta x. To get to the third one, it'll be A plus 3 delta x, and so on and so on and so forth, right? We're going to add, what we're going to add is we're going to add A plus ix. Right, where I is a counter, right? I is going to equal 1, 2, 3, so on and so forth up till n. And so each individual one will be a, each xi will equal a plus I times delta x. All right, and that's just basically what that allows us to do, is that allows us to select each one of our values for each one of our x values. Okay. Now the next thing that we need is we need each one of these f of x values, because that's going to give us our heights. Our heights are each one going to be an f of x, so they're going to be f of xi. So this is our intervals will be at each xi, and our heights, okay, will be f of xi star, which is essentially f of a plus I delta x, since we're going to use right endpoints. All right. So when we constructed this area, the area was going to end up being written like this. It's going to be the sum I equals 1 up to n of f of xi, so that's a height, f of xi star rather, times delta x. Okay, and here's our height, and here's our width. And so that's the area in terms of rectangles. So that's all of our areas in terms of rectangles. What I'm now going to want to do, the simple part here, or maybe not so simple, is to think about this and say, okay, well, how do I represent making each one of those rectangles smaller and smaller and smaller and smaller, right? How do I get them smaller? And the way that I do that is I make the integral of f of x dx. That's going to be the one where we have basically tiny, infinitely small little rectangles that we end up accumulating over an entire line. is going to end up equaling the limit as x approaches infinity of this summation. That's the summation of I equals 1 up to n of f of xi star times delta x. Okay? And so what this is, right, the area when I have an infinite number of rectangles. And if you think about that, what's going to happen there is each one of them is going to become really basically very, very narrow, okay? But they're going to fill in the entirety of the area under the graph, right? And they're going to do it perfectly. So they're going to be a perfect estimate. They're no longer going to be an estimate. They're going to actually be the area under the curve. So this integral of f of x dx is literally going to be this limit as, not x approaches infinity, but n approaches infinity, of the sum of I equals 1 up to n of f of xi star times delta x. Okay? And what you're going to see here, and we're going to see this in just a moment as we do more of the algebra, is this I here, it's going to be the counter for the xi's. Okay? So it's going to tell me how many, I. It's going to basically be like what we end up using for the summation, right? Xi 1, 2, 3, etc., etc. And then what we'll do then is we'll get some value in terms of n, and then we'll just take the limit as n goes to infinity. Okay? And that's exactly what we're going to be doing. So now let's get in the nitty-gritty of how to actually evaluate these things. So I'm going to keep this definition of the definite integral along the top, okay, so you can see it. And let's say, for example, that what I want to do is I want to find the integral from 1 to 5 of x plus 2x cubed dx. Or 2x squared, 2x squared dx. All right. Now what I need to do is I need to turn it into the definite integral. Okay. I want to turn it into this definite integral. And so what I'm going to do first is I'm going to find that delta x. So I'm going to get delta x equals b minus a, equals 5 minus 1 divided by n. So b is 5, top of the interval. A is 1, bottom of the interval, divided by n. And then xi star is going to equal, and this will be a is 1 plus, okay, it's 4 over n, plus 4 over ni. And then f of xi star is going to equal 1 plus 4 over ni plus 2 times 1 plus 4 over ni squared. Okay? And if I wanted to, what I could do is I could just actually, I could factor this all out, or I will distribute it all out. Notice that what I've done here is I've inputted in xi star in for my x's inside of the function. So the xi star has gone into the function as its x's. And so this is going to give me then 1 plus 4 over ni plus 2 times 1 plus 8 over ni plus 16 over n squared I squared. And then simplifying a little bit more, we're going to get 1 plus 4 over ni plus 2 plus 16 over ni plus 32 over n squared I squared, which is then going to be equal to 3 plus 20 over ni plus 32 over n squared I squared. Okay, and so that's our f of xi, and that allows us to actually fill in the entirety of this definite integral. So now let's take this information and find a value for the definite integral. So our integral from 1 to 5 of x plus 2x squared dx is going to then equal, and we'll make this the summation, or the limit, the limit as n approaches infinity, because we're going to go back up here to that definite integral definition of I equals 1 up to n, and then we'll plug in f of xi. So this will end up being 3 plus 20 over n I plus 32 over n squared I squared times 4 over n, because that's the value for delta x. then what I'm going to do now is I'm going to let this equal the limit as n approaches infinity. I'll pull out my 4 over n because I can do that with summations. And then this will be times the sum I equals 1 up to n of 3 plus 20 over n I plus 32 over n squared I squared. So what you'll notice here is that in the case of the summation, the variable is actually I. It's not n. And so n actually ends up being a constant. It's some kind of constant term, and so we can bring it out. It's allowed to come out. That's why we pulled the 4 over n out towards the front. It's allowed to come out because it's not actually part of the summation. It's like something that's being multiplied by every summated term. Okay, so you can bring that constant out. And so this is then going to equal, and what I know about summations is that I'm going to be able to separate them out, right? Okay, make this into 3 separate summations. So this could be the sum I equals 1 up to n of times 3 plus, and then I can pull out the 20 over n times the sum I equals 1 up to n of I, okay, plus 32 over n squared times the summation of I squared. I equals 1 to n. Okay, so in each case, we separated out each individual summation because we're going to need those to do some simplification. And we pulled out the constant terms, the 32 over n squared, the 20 over n. We could have even pulled out the 3, but we don't actually need to. So now, what I want to get here is we've got some rules for summations that you should know. One is that the sum I equals 1 up to n of I is going to equal n times n plus 1 divided by 2. Secondly, the sum I equals 1 up to n of I squared is going to be n times n plus 1 times 2n plus 1 divided by 6. And 3, if we have some constant a, or call it c is a constant, okay, then this is just going to equal cn. All right, so we're going to use that in order to simplify here. This is then going to equal, right, and we'll now move down, so now we can utilize these terms to let this equal the limit as n approaches infinity of 4 over n times, and this will be 3n, because that's a constant times in the summation, so 3n plus 20 over n times n plus 1 divided by 2, and that's because that's the summation I equals 1 up to n of I, plus 32 over n squared times n plus 1 times 2n plus 1 divided by 6. Close brackets. Cut, cut, cut. This will then equal the limit as n approaches infinity, and we're going to get 4 over n times 3n, so that's going to end up being just 12, plus, and then we're going to take 20 divided by 2, that's going to be 10 times 4, so that's going to be 40 times, and then our n's are going to go away, it's going to be 40 times n plus 1 over n, plus, then we're going to have an n squared, we're going to remove one of those n's, okay, so this just gave me an n, but then we're going to multiply it by n squared again, so the bottom is going to give me 3n squared, because I'm going to factor out a 2, and a 2 out of the top and bottom, so that gives me 16 times n plus 1 times 2n plus 1. And all that then multiplied by 4. So this is actually then going to be 64. So you got the 4 here. 4 times 16 is 64. 4 times 10 is 40. 4 times 3 is 12. And then we basically just factored out some of our n's. This is now going to equal the limit as n approaches infinity of 12 plus, this will be 40n over n. So that's just going to be 40 plus 40 over n plus, and then this is going to be 64 times, and this will be 2n squared, so we'll make that 128n squared over 3n squared. So it's 128 over 3 plus, and this will be then, the second part is going to be 3n, because that's 1 times 2n plus 1n, that's 3n. It's 3n times 64, that's going to be 192n over 3n squared, so it'll be 192 over 3n. plus, and then 1 times 1 is 64, so 64 over 3n squared. Now, when we take the limit as n approaches infinity, this is going to go to 0, this is going to go to 0, this is going to go to 0. So all three of those are going to 0, so this is going to end up being 12 plus 40 plus 128 over 3. And then that then gives me in total 94 2/3. And that's the value of my definite integral. So the process is involved, okay? It's pretty simple to set up the problem, all right? So the setup of the problem is basically you take these definitions of delta x equal to b minus a over n, and xi star is a plus delta x. Then we'll transform this definite integral, the integral here, into the definite integral, the definition of the definite integral, which is this guy right here, okay? So we start out with that whole process, and then it's a matter of just being really, really careful with your algebra, right, and with your summations, knowing that we can pull out the over n terms, okay, anytime we want to, and separate out our summations, all right, and knowing these three very important identities. Okay, those three very important identities will help us work with the definite integral. Okay, go through, lots of simplification, and finally we end up with the value of our definite integral. Okay, and that's how we go about doing definite integrals, and that's what it means to be a definite integral. Okay, so this is kind of complicated. It's a harder aspect of working with integrals. Like once we get past this piece, you get into antiderivatives and things get a lot easier. Okay, but you know what? This is a big part of math. You're going to have to know that basically what you're doing when you find an integral is you are taking an infinite number of sums of these little tiny rectangles. Okay? So this completes the lesson.